Greetings from a very cold and frosty Canberra evening here. As a bit of introduction, both myself and my co-author Karen Paul have for a number of years been working with the Australian government on improvements to the national greenhouse gas accounting system, in particular the full CAM model, which I'll talk a little bit more about shortly. But as scientists, obviously we're not responsible for generating national scale accounts. That's the responsibility of what will become on Friday a brand new department here, the Department of Climate Change, Energy, the Environment and Water. We just had a change in government, and departmental restructuring straight after an election is always quite interesting. It can tell a lot about the intentions of the incoming government, and I think making climate change front and centre of the new department name, I think, is quite significant and welcome. So the reporting, as people are probably aware, to the UN occurs annually. There's a two-year lag with the reporting, and the most recent report's shown on the slide there for anyone who would like to bore themselves silly by looking that up. For the land sector part of the accounts, there's a couple of key components there. One is the full CAM model, which I mentioned before, and the other is the use of Landsat imagery for detecting land cover change. And I believe that when that was first developed back in the late 90s, early 2000s, covering all of continental Australia at 25-metre resolution, I think it's one of the largest remote sensing activities that were undertaken at that time, and it's continuing through to today. So what I want to quickly run through in the time that I've got is to just briefly outline how biomass in Australia's national accounts is handled. Then I want to briefly outline some current work we've got on planned improvements to that, which is directly relevant to the topic of this meeting. And I'll finish with a slide addressing some of the requirements of that work and the potential role and linkages with CCI and the global biomass products. As Peter Scarth noted yesterday, biomass in Australia is extremely diverse. We range all the way from lush, temperate tropical forests all the way through to deserts with everything in between. So that can make things quite challenging. This is a very simplified representation of the full CAM carbon model. And in many respects, it's very similar to dozens or even hundreds of other terrestrial carbon models that you can find around the world. In full CAM, total above ground biomass, or more accurately, increment in above ground biomass, is partitioned into a number of living biomass components. They're labelled in green there. That requires converting from biomass into carbon in the usual way, but it also requires expanding the above ground biomass to include roots through sets of root-shoot ratios applicable to different vegetation types. That living biomass is eventually senesces and passes into a range of debris pools in the orange, and then into the Roth Sea soil model depicted in brown there. And then, as usual, there's continuous losses of carbon back to the atmosphere through decomposition, and then instantaneous transfers and losses resulting from things such as fire and harvesting and other disturbances. So in the current system, biomass is predicted from a really very simple empirical model called the tree yield formula. And I've drawn that there with the blue curve, and that's a smooth curve in the figure, but you can imagine that if there was fire or harvesting in that history, that would be depicted in that figure as well. But just a smooth curve for simplicity here. So the three key parameters, one we call M, which is the ceiling or the maximum biomass that can be attained at any given location, and that little map at the bottom there is a map of that parameter. Another parameter we call G, which changes the initial slope or rate of biomass accumulation, and another parameter R, which raises or lowers that M value as required. For example, plantation forests often attain greater biomass than the native vegetation they replace, and that's a simple way to recognise that. Couple of things to note. One is that those growth parameters, the G and the R, they're calibrated to a discrete number of vegetation classes, and thus the biomass predictions coming out of the simple model represent the average growth potential representative of each of those classes. And like many of these large-scale continental models, they're reasonably accurate at regional or continental scales, but highly uncertain at any given location. And that's in somewhat contradiction to the increasing use of this model for project scale accounting in Australia. And that's obviously quite challenging for non-modelling folks like landholders to get their head around that. You know, that they can go out and they can see that the model prediction is clearly wrong for their backyard, but yet they're kind of told, well, that's okay. It's okay for the model to be wrong at your location, so long as it's accurate over larger scales. That doesn't really sit well with most people, because if they see the model's wrong, then the conclusion is that the model's wrong and it's rubbish. So that's quite a communication barrier. So to help reconcile some of that, and for other reasons, the proposal is to move the system away from the simple model through to something that's informed more directly by remote sensed data to provide greater local relevance and accuracy. So in simple terms, the idea is to replace that simple model with a model that's based rather on combining various remote sensing data sources with field-based observations to develop a series of field-calibrated canopy to biomass models. So that's the idea. And the initial focus here is just arid and semi-arid Australia with sparse trees and open canopies where we think we might have more success, at least initially, in trying this approach. I'm not going to say anything about the methods that are going into that, mostly because it's a bit out of my area of expertise, so I'd probably make a hash of it if I tried to explain it anyway, but also because this is still very much a work in process. And this has been led by our colleague Peter Cachetta in Perth and his team. I will briefly mention the fieldwork component that's going along beside this. So to provide this link between field measured biomass and cover and the remote sensing modelling side of it, we've been sending our field crews out all across Australia for the last couple of years to collect new data specifically for this task. It's been quite an amazing outcome, actually, given that it was in the middle of a pandemic and we were able to still get our crews out there. So we've completed 48 sites across the continent, you can see on the map there. And at each of those sites, we've got about 8 to 10 90 by 90 metre plots. We've undertaken a range of measurements. In direct contradiction to Ron's advice yesterday, these plots were not selected as part of a probability-based sample. These were deliberately selected to ensure that we sampled the greatest variation in canopy characteristics at each of those sites. So within each of those 90 by 90 metre plots, we measure all individuals, measure their diameters to feed into our allometric models for estimating biomass, as well as direct measurements of canopy cover and height to provide that hook into the remote sensing analysis. I'll just add here that NISAR team has been in contact with us, and I think it's already been done, or we're currently negotiating data sharing agreements so that this data can be utilised more broadly than our specific use as well. Just my last slide, a bit of a summary of the requirements and the connections. So first of all, the requirements. So it's clear that above ground biomass is the thing that it's of interest to us here, unconfounded as much as possible by debris, because we want to avoid double counting, because the debris is handled by the full cam model itself. So if that's embedded in the signal coming out, then that's not a good thing. The spatial resolution is tied to the current national inventory workflows for detecting land cover change. So that's using the Landsat imagery around 25 meters. We're aiming for an annual temporal resolution here, at least initially. And also to be consistent with the rest of the world, I guess we're looking to provide estimates of uncertainty with that product as well. And here I'll just re-emphasize Ron's point he made yesterday around the importance of including pixel level pairwise covariances in that total variance term. when you're using these model-based variance estimators that we will have to use here, given our sampling design. It's something that I confess that I haven't included in the past when I've dabbled in this area. But if you do read Ron et al.'s last paper, you'll see why this is really important if you're aggregating things up across space and adding things up across multiple pixels or map units. It's really very critical to do that. Otherwise, you're likely to end up with probably a fairly gross underestimate of what the total uncertainty might be. A couple of side notes at the bottom there. The one I mentioned there is the current focus is on the arid and semi-arid areas. The last one there I'm going to mention and then run away from because there's a double can of worms in that one. And that's the fact that we're not just looking to get static biomass maps here, we're looking at biomass change, and that adds a whole different or whole new level of complexity for detecting change. And then the other side of that is that we also need to attribute that change for national accounting. Obviously, we need to separate anthropogenic from the non-anthropogenic, and that in itself is a pretty nasty problem. I'll just leave that one there. On the connection side of things there, I've listed 4 possible touch points, but there are probably many others that I've overlooked, and I'm sure if I canvass this talk more widely than I did amongst my colleagues, there'd be another list added to that, but it's a starting point. The first is fairly obvious, and that's the use of the global products as described in the last, or yesterday and today, to be used and to inform the modelling that I just described, and that includes the fire products that we just heard about as well. The second part of that is around using some of our products to help the global effort, and I already mentioned the link to the NISAR work that we've already established. A third potential touch point there is around the gap filling of our closed forests. We're just closed canopy forests. We're just focusing on the arid and the semi-arid to start with. So there's possibly a potential link there for I guess gap filling with the global products, which are more comprehensive in their coverage. And just a final comment there, just to pick up on Martin Brandt's talk yesterday around the individual tree canopy work. We've just got a project up and running with the team, with Tim McVicker, who I work with, and the Australian National University. Got a postdoc to roll that technology out across Australia as well. That's clearly a relevance here too, but perhaps it's a little less clear at this stage how those bits could all fit together, but it's clearly really quite relevant. That's all I've got, Martin.